teacher in charge, Monica, all the faculty members for their constant support and also organizing such a wonderful job. In this series, they have already organized 3, and this is the 4th in the series. The unfolding mysteries of space. Unfolding mysteries of space. That space is such a fantastic, such a vast, such a fantastic dimensions that defy imaginations. We talk of Earth, the planet, we talk of solar system, we talk of star system, we talk of galaxy, and then there are millions and billions of galaxies, and probably there's no end. Man is always curious to know more and more about the space, more and more about the universe, and people start talking now, it's not universe, it's a polyverse. And of course, it's too elementary, I know. All of us are eager to hear Dr. Priya Hassan, and without taking much of the time, I give this platform to her, and over to you, Monica. Thank you.
Thank you, sir, for your motivational words. Science is a way of life. Science is a perspective. Science is the process that takes us from confusion to understanding in a manner that's precise, predictive, and reliable, a transformation. For those lucky enough to experience it, that is empowering and emotional. With these words, I would like to invite our respected teacher in charge of Department of Physics, Dr. Kakuli Bera ma'am, to welcome and introduce our guest speaker. Over to you, ma'am.
Thank you, Dr. Monica Sharma. Thank you, Kamal sir. Good morning to all of you. I, Dr. Kakuli Bera, on behalf of Physics Department, Deshbandhu College, University of Delhi, welcome our Principal Sir, Professor Rajiv Agarwal, Vice Principal Sir, Professor Kamal Kumar Gupta, Distinguished Speaker, Dr. Priya Hassan, IQAC Coordinator, Dr. Aditya Saxena, DBT Star College Scheme Coordinator, Dr. Indrakant Singh, Physics Society Convener, Dr. Pankaj Singh, all faculty members of our college and from other colleges, all the participants, all the research scholars, and all the students in this interesting and motivating talk on unfolding mysteries of the universe, James Webb Space Telescope by Dr. Priya Hassan. It's a great pleasure for me to introduce Dr. Priya Hassan to all of you with her brief academic record. Dr. Priya Hassan is an assistant professor in physics at the Maulana Azad National Urdu University, Hyderabad. She did her integrated masters from the Moscow State University, Moscow, Russia, PhD at Osmania University, Hyderabad in 2004, and postdoctoral research work in France and in Ayuka, Pune. She was awarded the Woman Scientist Award by DST in 2006. She has presented her work in various conferences in India, Europe, and US, and in the United Nations, Vienna. Her research interests are in observational astronomy, star formation, star clusters, and galaxies. She is actively involved in Olympiads, public outreach, and science popularization programs, and has worked on various projects with the International Astronomical Union and Office of Astronomy and Development, US Consulate, Hyderabad, etc. She is the co-chair of the Women in Astronomy, WG Working Group of International Astronomical Union, and the member of the Public Outreach and Educational Committee, Astronomical Society of India, and ISDT TMT. Now it's my great honor to welcome Dr. Priya Hassan for her talk on Unfolding Mysteries of the Universe, James Webb Space Telescope. Welcome, ma'am. Over to Dr. Priya Hassan, ma'am.
Thank you, Dr. Kakuli Bera. Thank you, Monica Sharma. And thank you, Rajiv Agarwal, for inviting me. Thanks, everyone. Thank you very much. I start? Yeah?
Yes, ma'am. You.
So I'm sharing my screen, and please let me know if all's fine. All good?
Yes, ma'am, it's visible.
Okay, thank you. So, hello everyone, and once again, thanks so much for inviting me to talk. And that's why today, when I had the choice of topic, I took up the topic of the James Webb Space Telescope because that's so much in the media. I'm sure you've been hearing a lot about it, and therefore, I thought this was a very good opportunity to give people a chance to understand what's all the big noise about and why are we so excited about the James Webb Space Telescope. So let's start with it step by step. So the James Webb Space Telescope, in simple terms, if we were to say what is James Webb, it is basically an infrared space telescope. And now I'm going to try to, the rest of the talk, that's what it's basically all about. I'm going to talk about what exactly do we mean by these things. So first of all, we'll try to understand what is a telescope. Then we try to see what is infrared, why do we want it in infrared? And then the other most important thing is what is a space telescope? What is the basic purpose of sending telescopes to space? Why do we want to do that? So we'll come on step by step with each of those things. So the simplest thing, let's go on to it, is what is a telescope? Telescope is basically a tool that astronomers use to see far away objects. So what do we basically do in this? If you see in this picture, you have a mirror. There are different kinds of telescope. This is just example of one kind of telescopes which are called reflecting telescopes, which have mirrors. You could also have a refractor telescope which has lenses. Okay, but since the James Webb is a reflector, I'm going to concentrate on reflecting telescopes. So typically what you can see in this image is you have a faraway object. Light falls onto this mirror. The mirror focuses the light, but if you were to observe it, you would have to see the focus somewhere over here. So instead, we have a second mirror over here, which deflects this light and sends it on the side from where you can observe it, right? So that's essentially what a telescope basically does. It's a light collecting bucket, right? So what happens is, you know that our eyes have barely, the size of the pupil in our eyes is barely 2 millimeters. That's the size that we collect light in. But in this case now, since we have a big mirror or a lens, in that case, the size of this mirror is much, much larger, right? So for example, for this James Webb telescope, it's 6.5 meters, right? That is the size of the telescope. So what you do is instead of having your 2 millimeter pupil entry, you're having something like 6.5 meters to actually focus this light. So you are hence going to get, manage to collect much more fainter objects because of your larger collecting area. Now, the first one to actually historically who has been credited for using astronomy, using telescopes for astronomy is Galileo, more than 400 years back. And what he did is the telescope that Galileo used is shown here in this picture, which you can see is very small. But in principle, in spite of that, the results that Galileo got, even by looking through such a small telescope, were path-breaking. For example, he saw the craters of the moon, which is fine. Then he also saw the satellites of Jupiter. Now, remember, this was the time when you had the geocentric theory. That means the belief that the Earth is the center of the universe. But suddenly he could see there were these satellites which were going around another planet, which was Jupiter. And so he could see another system which was other than ours. So that was already questionable points against the geocentric system. The next thing what he saw is he saw the phases of Venus. And in the phases of Venus, he could actually, the only way one can explain the phases of Venus is if you have an inner orbit of Venus, right? And that means it has to have an orbit inside the orbit of the Earth. And that could be only explained if you had a heliocentric system, right? So then he also pointed the telescope onto the Milky Way where he could resolve it to stars. And therefore, what Galileo got 400 years back also by observing through his telescope were already milestone discoveries for which obviously he was not too appreciated by the church because these were against the geocentric system, which was against the belief of the church at that time. And so basically, this is just to convince you about the importance of the use of the telescope, of how even a small telescope could actually change things so drastically in the field of astronomy. Now, like I mentioned to you, there are reflecting as well as refracting telescopes. We won't go much into the detail of this, but here what you're seeing is you basically have a mirror, the mirror which collects the light, and then you could either observe this at the prime focus. So if you had the focus somewhere over here, I'll show you an example of that. And then in the bulk of telescopes in today's times, you don't observe with the prime focus. You have a secondary mirror which redirects the light to another point, right? So the advantages of this is, so here you can see an animation of the thing, and we don't have much time to get in details, but typically a reflector telescope has the advantages that there's no chromatic aberration, because reflection it's independent of wavelength, right? And in that sense, you have to only have one surface which is perfectly polished. It can be made larger, lighter, and cheaper. And therefore, all large telescopes of today, not only the James Webb, but even the other large telescopes that are being built, all of them are reflecting telescopes. That means they are made up of mirrors for these simple reasons, right? So now here's an example. This is Mount Palomar, which was made in 1948, which was one of the largest reflecting telescopes. It has a size of 5 meters, okay? And actually you can't see, this is the counterweight, which you're seeing. The telescope is this. And in this telescope, what you actually had is that people actually sat in a cage, which was at the prime focus. And in that way, they had to observe, right? So that was the first design I'd shown you, where you have the telescope mirror over here and the observer sits at the prime focus. This, what you see, is just a counterweight, okay? It's used to balance the telescope. It's not the telescope, this thing which you see over here. And then gradually, people obviously started building larger and larger telescopes. So you had the Keck telescopes, which are amongst the largest and the most efficient optical telescopes in operation at present, which were built in 1996. So these are 10-meter telescopes, 2 of them. And what's very interesting in them is that you have 2 telescopes in optical, which actually do what is called interferometry. And interferometry is a very powerful technique to increase the resolution of a telescope. Now, the other job of telescopes, other than collecting light, is to resolve, that is to see sharper objects. And obviously, it's limited by the wavelength, and it's limited by the diameter of the telescope. And therefore, what happens is, if you increase the diameter of the telescope, you can improve the resolution of the telescope. And that's basically done by this technique, which is called interferometry, where you actually use the 2 telescopes like an interferometer. Now, this was used a lot for radio telescopes, but doing it with optical telescopes is a far more difficult job, which is done at Keck. Now, there's this site at Mauna Kea. So what we need to do when we look in optical, we have to basically look for sites which have good seeing. That means for which the skies are clear and there's lesser water vapor. And so there are typical sites which are very good for astronomy, with which you can observe very well. So this is a site which is at Hawaii, which is called Mauna Kea. And here you have amongst the world's best telescopes located over here. The other important site for observatories is Chile. So Chile is in the desert, Atacama Desert. So you have, again, a lesser amount of water vapor, and that is also used. But that is a southern hemisphere site. This one is the chief northern hemisphere site, which is in Hawaii. And then people have obviously been building bigger and bigger telescopes. So these are the ones which are in the pipeline. There is the giant Magellan telescope, which is being built, which is made up of 7 mirrors. There is the European extremely large telescope, which is 38 meters in size. And then there's the 30-meter telescope, of which India is also a 10% contributor. We are contributing 10% into the 30-meter telescope. This has also been built in Mauna Kea, Hawaii, the TMT. The ELT is being built in Chile. So that would cover the southern hemisphere. And just to keep you all informed, there are a whole bunch of observatories which we have in India also. There is this one, which is called the Japal Rangapur Observatory, which is not very far from Hyderabad, about 60 kilometers from the city. There is Nainital, which is quite close for you all. Most of you all, if you are in Delhi, if you go to Nainital, Nainital has a telescope over here. So 1.3 meter telescope. And this is at Manora Peak. This is another telescope, which is the IGO. I made a mistake. This one is the Mount Abu telescope. This is Miro. I made a mistake. This one is the Ayuka telescope, the IGO. And this is one of the largest telescopes we have at present, which is the Himalayan Chandra telescope, a 2-meter telescope, which is at Ladakh. The largest optical telescope at present in India is the 3.6-meter telescope, which is at a place called Devasthal, not very far away from Nainital. So over here, what you can see in the picture, this is the 3.6-meter telescope, which is already operational. There's a liquid telescope, which is also being made over here, 4-meter, and there's a 1.3 meter, right? So these are the top telescopes we have in India. Now, we'll compare these, for example, with space telescopes. So in a minute, I'll explain to you why do we want to send telescopes in space. But you can see over here examples of telescopes in space. And here comes the James Webb, which we'll be talking about very soon. So the other important thing, so what this covers the telescope part. The other important thing is about infrared. Now we know that in the electromagnetic spectrum, this is the electromagnetic spectrum, there's a very small window, which is the window of visible light, which we can see with our eyes, right? So our eyes are detectors only for this small window, which is about 3000 to 8000 angstroms, okay? That is the window which we can see with our eyes. We cannot see radiation in these other wavelengths, okay? But the problem is that visible light is only a very small part of the electromagnetic spectrum, and different physical processes, okay, they emit in different wavelengths. And therefore, if you want to study different physical processes, it is very necessary for you to study other parts of the electromagnetic spectrum, right? So for example, if you're looking at X-rays, these are high energy radiations. So typically, if one is looking at black holes, for example, you will need to observe these with X-rays because these are high energy radiations. Similarly, there could be parts of the radiation which you want to observe with infrared, which is the cooler part of the universe, or with a radio, which will show you gas. And therefore, the problem is that what is visible with our eye is limited. We want to actually study more physical processes which are not visible to the eye. So one example of this is the infrared. And now I'll tell you why is infrared so very important. Infrared is very important for the simple reason that, first of all, most of you all, since you're physics students, you would be aware with Planck's blackbody spectrum. You know that the radiation coming from a hot body follows this kind of a law, which is called Planck's blackbody radiation. And the peak in the radiation depends upon the heat, the temperature of the object, right? So if the object is hotter, the peak will be closer to the X-ray ultraviolet side. But if the object is cooler, it will be more towards the infrared side. Now, for example, if you look at this thing over here, you can see that infrared radiation is the radiation. Even we are very good infrared emitters. It is the heat which you can get from, from radiators, etc. Different parts of the electromagnetic spectrum are used for different purposes. And very soon I will tell you why is infrared so important and so interesting. Now, infrared basically covers wavelengths from 700 nanometers to 1 millimeter. And we just in a minute, I'll tell you why is that so important. But the other problem we have is our atmosphere. Now, our atmosphere works like a kind of a blanket, okay? It is the very important thing which sustains life on the Earth, right? For example, one of the biggest problems with life on Mars is the fact that Mars has a very thin atmosphere. And therefore, for life to sustain itself, it would be very, very difficult because you hardly have an atmosphere on Mars. Now, the Earth's atmosphere also is a very thin layer. You can see it's a very thin layer. But that's what very much protects us from radiation that comes from outer space. So if you actually look at this thing, this is a picture which actually shows you what is the penetration or the fraction of radiation blocked by the atmosphere. So you can see that we should be very thankful that our atmosphere actually totally blocks X-ray and ultraviolet radiation coming from the cosmos. And that would be very harmful for life, right? So that's very good for us. It lets in light from the visible window, some pockets in the infrared windows as well as the microwave window. And the largest window which we have is the radio window. And in this window, it's completely transparent. And radio wavelengths are not harmful for light. They are longer wavelengths. And that is why that's what we use for communications, because this is the largest transparent window of the electromagnetic spectrum. Now, if you notice that the infrared has pockets, that means there are parts of the infrared which are visible, but there are many parts of them which are blocked. So if you see this very big part, this one is blocked. You have some parts over here which are penetrable. Now, just once again to convince you, why do we need to look different at different parts of the electromagnetic spectrum? If you look over here, you can see images of, for example, the galaxy in different wavelengths. And different components of the galaxy, they emit in different wavelengths. So for example, if you see the galaxy in the radio, you are going to get the gas component. The visible will be the stars. The X-ray will be the high energy radiation or the hot gas. And infrared will be the cold gas. And therefore, if I want to study different components of the galaxy, I have to actually observe it with different eyes. By different eyes, I need to say in different wavelengths, right? And here's another example of a galaxy, which you can see in different wavelengths. You can see that in radio, you can see the cold gas. In infrared, you can see the cold stars. In optical, you can see the sun-like stars. In ultraviolet, you see the hot stars. And in X-ray, you see the hot gas. So if I want to make a complete picture of the galaxy to understand it, I obviously need to observe it in all parts of the electromagnetic spectrum so that I can characterize components of the galaxy. So this is something like the blind man or woman problem, where if we are trying to put in this jigsaw puzzle of understanding the working of our galaxy, what is actually happening in the galaxy, we need to parallelly study the stars, the gas, the dust, the hot component, the cold component, and put it all together to understand the galaxy. And so what you see, it's like this blind man's problem or blind woman problem, where if you only were to only study optical radiation, you would only see one component of it, probably, for example, the tusks, where you would say that's the sphere. But if you observe other components, for example, the radio, the X-ray, and infrared, you will see the complete picture of the galaxy, which is very necessary. And therefore, we would like to look at our galaxy or different objects in different wavelengths. So that is one of the reasons why we need to go out in space. Because if you remember, I showed you the picture, our atmosphere blocks ultraviolet, X-ray light, part of the infrared. And therefore, if I want to observe these components of the, observe them, I have to go out to space. You have to go outside the atmosphere so that you can observe it, right? Now, officially, the Kármán line or the definition of space is a height of 100 kilometers. So if you go above 100 kilometers, you have actually gone into space. So that's what we basically need to do, is send the telescope to space so that we can observe the wavelengths which are blocked by the atmosphere, right? And that's why we need to send the telescope to space. The other very important reason to send a telescope to space is the atmosphere itself. It does something what is called spoils the seeing. In astronomy, we define something called seeing, which is our capacity to see an object. So for example, if you look at a star, right? If you look at a star, you know that stars twinkle. Now, stars twinkle basically because there's a slight, if you look at the atmosphere, there are components in the atmosphere where there's turbulence. And due to that, the position of a star slightly shifts. And that shifting is what we call twinkling, right? And if there's a lot of disturbance in the atmosphere, you will see a lot of twinkling. And you won't be able to see the star very clearly. And therefore, if you let's look at this object, you can see that there's a single star, but because of turbulence in the atmosphere, you are going to see multiple images of the star. And these multiple images shift at a very high rate. And therefore, what happens is your cumulative brain thinks that this object is so large and so fuzzy. It's not with clarity. If I add a telescope, I will be able to magnify it, right? I will be able to put it better, but still there is this shifting of the image which is caused by the atmosphere. So here down you can see an example of, here's an image of Jupiter where you can see this is with clarity, but here is if you have a turbulent atmosphere, you will see it fuzzy like this. You will not see clarity. This is what we call loss of resolution. So if you look at the left-hand picture over here, you can see these set of stars, but they are unresolved because the position of these stars have got shifted. And as they get shifted, you get these blobs. But if I stop the shifting, you will see more clear images, which are the ones over here. Similarly, here I have examples of others where if you're improving your telescope, you can basically improve the resolution. So this is the Hubble Space Telescope, 2.4 meters in space. This is the VLT, and then there's the ALT. So that's the kind of improvement you expect when you add a telescope. So a telescope actually does try to solve this problem of turbulence of the atmosphere, though it does it only partially. Because number one, the thing is you look for a good site, like the Mauna Kea site or the Chile site, where you have a better sky. And the second thing, you have a larger telescope, which will improve the resolution so that you have less of this shifting, so that you can see it well. So you can see there's a difference which is expected. This ELT is ground-based simulated image. VLT is also ground-based. So you can see that there is an improvement, but obviously there's a limitation because of the presence of the atmosphere, right? And therefore, the other, so like if you send if you send the telescope out in space, then you will still have a problem with seeing, but this is what we call diffraction limited seeing, because you know that light is a wave. So anyway, there is going to be some kind of diffraction taking place, and you will observe a diffraction pattern, right? If the telescope is out in space, but that diffraction pattern is very small because it is only a function of the wavelength, right? And therefore what happens is you still have a problem, but it is what we call diffraction limited, not too large, not a very big problem. And therefore, to sum it up, let us see, why do we need to send the telescope in space? First of all, is because certain wavelengths like X-ray, gamma ray, ultraviolet, mid-infrared, far infrared, they can only be accessed outside the atmosphere, right? And in the outside the atmosphere, you will have only what we call diffraction limited seeing, but is right, that's the other advantage. The other advantage is that ground-based telescopes have limited observing time because of Earth's rotation, right? Because you have day and night cycle. But in space, what happens is you can actually look at the same object night and day. There is no problem. And that's the advantage. Now, space telescopes are often classified as, they are what are called survey mission. They could be meant to survey the sky, or there are what we call targeted ones, right? So James Webb is targeted. We'll come on to it. There are some disadvantages of space telescopes also. The biggest disadvantage of space telescopes is that space telescopes are expensive, right? Because you need to launch the telescope, send it out in space, which obviously costs a lot more money than it would if you were, if it is a ground-based telescope. The other big problem with space telescopes is that because of their location, they are very difficult to maintain, right? In the sense, the Hubble Space Telescope has had a whole bunch of, missions to actually servicing missions, but otherwise, every servicing mission also costs a lot of money, and most space telescopes, we cannot have the luxury of actually doing a servicing mission. That's the other problem. But a long time back, this is more than almost 100 years back, people had already thought of the advantages of sending telescopes in space. And we had these two people who had actually thought of having an observatory on the moon, because the moon is close by, the moon has a thin atmosphere, and that would be a good vantage point. And, then even Spitzer, a whole bunch of people also proposed telescopes in space, basically because of the advantages I told you about. And these are a whole bunch of a set of space telescopes that have been sent. We don't have time to get into the details, but just to tell you that we have a large legacy of the amount of space telescopes that have already been launched. And then the most well-known space telescope that most of you all would be aware of is the Hubble Space Telescope, right? And you can see over here, this is the Hubble Space Telescope, which was launched by the Space Shuttle, and this is 1995. Okay, and then, for example, to observe an X-ray, there is the Chandra Observatory, which is still operational, and it observes an X-ray. And we don't have the time, but there are a whole set of very interesting results which have been obtained even from Chandra. This is by observing these objects in X-ray. Like I told you, then you're getting the hot component of the universe, the high energy components. And for gamma rays, there's another observatory called the Compton X Gamma Ray Observatory. To observe in infrared, we had a telescope called Spitzer. Spitzer has a size of about 0.85 meters. That was the size. So it's a small telescope, not a very big telescope. And it basically observes in wavelengths from 3.6 to 160 microns with a few instruments. And Spitzer has come out with some very interesting results. After Spitzer, there was another telescope which was called the Herschel. Herschel is a 3.5 meter telescope, and which observed in the far infrared and sub-millimeter wavelengths, also which gave very good results. And then there was the NASA Great Observatories program, where what they did is that they used all these big telescopes, for example, Chandra, Compton, Spitzer, and Hubble, to look at the same part of the sky and make studies of the same part of the sky in different wavelengths. There's also a dedicated telescope which is actually looking for exoplanets, which is called TESS, and it's a transiting exoplanet survey satellite, which was launched in 2018, which actually has identified more than 4,000 exoplanets. Before TESS, there was what was called Kepler. I'm sorry, the slide came later. So TESS was the successor to Kepler. Kepler is a 0.95 meter telescope. It's about a 1 meter telescope, which was sent in space specifically again to look for exoplanets in a certain part of the sky. Now, the other important thing is what we need to do in astronomy is what is called astrometry. Now, what you see on the right is the image of the Big Dipper. Most of you all may know this constellation. This is called Saptarishi, or the Big Dipper. And you can see that the Big Dipper, individual stars have their own motions, right? But if you want to measure those motions, you can see the timeline is put over here. So this is obviously, the motion is in thousands of years. But what you can see is that if we want to have kinematic information of stars, then you have to have very precise measurements of the positions of these things. So you measure the position today, you measure it say after a month, and you check the difference to get their velocities. And that's what's called astrometry. You're measuring the positions and hence measuring the velocities. And the first astrometric satellite was called Hipparchus. And Hipparchus actually did the job of astrometry for 1 million stars. It measured the positions and velocities for these millions of stars. And the successor to that, so basically what it does is it measures space velocity. So for example, it measures radial velocity, that is the velocity in the line of sight. And it also measures what is called transverse velocity, which is the velocity of stars along the plane of the sky, right? And the present satellite, which you all must have heard about, is called Gaia, which is a satellite by ESA, the European Space Agency. And Gaia basically gives very, very precise measurements of the movements of stars. And not only stars, but all celestial bodies. It gives you a precision of, supposing you had a 1 rupee coin put on the moon and you were observing it, it gives you that kind of precision, right? When you're observing with Gaia. So Gaia is this satellite. So what you see is that by going out in space, like I said, one very big advantage is you are accessing wavelengths which are not accessible. You are also accessing, you are also getting the advantage of better seeing, right? Diffraction limited seeing. And then, for example, you also have a very big advantage of astrometry, right? Because your seeing is better, you can very precisely measure positions and hence measure velocities. Now, Gaia, the satellite, is placed at a position called L2. L2 is important because that's exactly where James Webb is. And these are called Lagrangian points. And I'll tell you what are Lagrangian points in a while. So this is another image of Gaia, which is basically showing you how is it very accurately measuring the positions, the parallax also of stars, which will give you the distance and the velocities of stars. So Gaia is a different story. We can talk about it on another time. Now let's just get back to Hubble. If you all remember, I just mentioned to you that Hubble is a 2.4 meter telescope sent out in space, which was sent out in 1995. Okay, and it has various instruments on board, and it's still very much operational. It has got very amazing results. We don't have the time to see it, but if you were to actually see this on the net, you can actually see images of the kind of brilliant images that we have got using Hubble Space Telescope. They're very beautiful images. And I'm going to skip that because we don't have the time. So that was Hubble, right? Now, James Webb Telescope was, so we finally come to James Webb. I have explained to you what's a telescope, what is a space telescope, and why do we need infrared. But infrared, I'll even still talk to you more about what is infrared is what we did. We'll talk about why do we need infrared. So James Webb Telescope was actually conceived in 1996. And the basic idea was obviously a jump from Hubble. So Hubble is 2.4, while James Webb is 6.5. But the basic purpose of James Webb is to study the origin of stars, galaxies, planets, etc., to do origin studies. So basically, and it's named after a NASA administrator, James Webb. Now, now what happens is, if we want to look at the universe, when the universe was very, very young, okay? So in the next slide, I'll explain to you that we have reason to believe that the universe is an expanding universe, right? Our universe is an expanding universe. I'll just talk to that in a minute. And because of that, Doppler shifts. You remember what are Doppler shifts? Is you have a shift in wavelength because of the motion of the source. And because the universe is expanding, the shift, it's moving away from us. So therefore, the shift is towards the red. So things which were emitting in the optical will now emit in longer wavelengths, which is, for example, the infrared, right? And therefore, if we want to actually look at a time when galaxies were young, we know that the universe has a age of approximately 13 billion years, right? So if we want to look at objects like that, these objects are already going to be emitting only in the infrared, right? What they were emitting in optical will now be in the infrared. So if you want to observe them, you have to observe in the infrared. Their emission, the original emission which they emitted, is now observable in the infrared. And obviously you need a large mirror because you want to see faint objects. And a lot of these young systems, for example, young stars, young planets, they are in dusty regions. And dusty regions have a large amount of infrared emission, because infrared passes through the dust. But optical light, you cannot see it through the dust. So if there is dust and there's optical light, you will not be able to see it. But if there's dust and there is infrared light, you can see it, because the scattering, this thing is inversely proportional to wavelengths. So longer wavelengths will have lesser scattering, you'll be able to see it. And so if you want to look back in the early universe, in star, planet forming regions, galaxy forming regions, dusty regions, we need to observe in the infrared. And therefore, James Webb was planned to have a larger mirror, which is 6.5 meters, as well as observe in the infrared, because the redshifted emission from these objects is going to be in the infrared, and that's where you will need to observe it. Now, obviously, such a project is a very expensive, big project. It costs $10 billion, and therefore it's an international project, in which the major contributors are the United States, Europe, and Canada. So essentially, there's space agencies, which is NASA, the European Space Agency, and the Canadian Space Agency. These are the three major contributors onto the James Webb. Now, in principle, many people think that the James Webb is the successor to Hubble. But in principle, it is not the successor to Hubble, because Hubble basically observed in the ultraviolet, in the optical, and very little in the infrared. But James Webb is essentially an infrared telescope. It does not observe in optical or in ultraviolet, right? It basically observes in visible and in the mid-infrared, right? So in principle, if you remember the other space telescopes I spoke to you about, it has a larger overlap with the wavelengths of Spitzer. You remember Spitzer was another space telescope I spoke to you about, and it actually overlaps more with Spitzer. But Spitzer was only 0.85 meters, and Spitzer is on a low Earth orbit, while James Webb is much further away, right? So in principle, James Webb is an improvement of Spitzer and not of Hubble, right? Now, the expertise in James Webb, because you want to observe in the infrared, if you remember, I told you that we itself are very good infrared emitters. The Earth also is a very good infrared emitter. There's lots of infrared emission coming from the Earth. And therefore, what happens is the expertise of these space agencies, NASA basically was handling the mirror, right? Because NASA has made a lot of mirrors, and it's also handling what is called the sunshade. James Webb has a very large sunshade, for the simple reason is that because you are observing in the infrared, you want the telescope to be very, very cold. We are going to talk about the temperature of James Webb, but we need the telescope to be very cold, and that's why we have a very large sunshade, right? ESA, the European Space Agency, basically did the launching. They have a launch site at Kourou in French Guiana, which is in South America, the northern part of South America. And they have that launch place over there. And so they were the people who launched the James Webb, as well as one of the instruments on James Webb called MIRI, which is the mid-infrared instrument. That's the one which was made by ESA. Canada, many of you all may not be aware of, but Canada actually specializes very well in, the robotic arms which are used in the space station. And, even in, there's a camera on James Webb, and even that's being done by them. Now, the cost of this is the telescope costs about 11 billion, of which 1 billion was just the cost of the launch, right, which was covered by ESA. And if you were to compare Hubble with James Webb, like I told you, Hubble is 2.4, this is 6.5 meters. And obviously the difference in that basically comes in your collecting area. So it actually goes as R squared, right? So if you were to put 6.5 divided by 2.4, you'll get about about 3, a factor of 3, and you square it. So that will give you the improvement which you're going to get in, in the improvement in the light collecting area of James Webb compared to that of Hubble, right? So that's the basic big improvement which you're getting using these things. I can see there are a few questions on the chat window, but I will just address it in a short while. Okay, just to let people, I'm seeing your questions, but I will just handle them in a short while. Yeah. Okay. Okay. So don't worry. You can continue putting your questions on the chat. I'd be very happy to answer them. I will just be covering them in a short while, right? So if you can compare, so like I said, James Webb was actually conceived way back in 1996, but obviously since it had a very large budget and planning it is not an easy task, I'll explain to you why. Hence the mission kept getting delayed and delayed and delayed, and that is why it finally just got launched so recently because of various problems with it. We'll talk about these things. Now, I'll just repeat this part which I was telling you, which I did not explain, was Hubble. Edwin Hubble actually is credited with giving us the idea of the expanding universe. So what Hubble basically did is he observed various galaxies, okay? And what he did is he did spectroscopy of those galaxies, and using that you can get the wavelengths of emission coming from different lines. And what was found by Hubble is that these wavelengths were shifted, they were redshifted. So all galaxies, almost all, showed a redshift, okay? You'd be surprised to know that the one that does not show a redshift is Andromeda. Andromeda is the closest galaxy to us, which is not redshifted, but is actually blue shifted. If it is coming towards us, it's not going away from us, right? But that's another story. But in general, what Hubble noticed is that all galaxies seem to be moving away from us. And that was actually the basis, the observational basis for the expansion of the universe. And using that, if you say that the universe is expanding at a certain rate, you can actually calculate what was the time when the universe was at one point before it started the expansion. And that would actually give you the age of the universe, right? So Hubble, you could get the Hubble constant, which is the factor by which the velocity is given. And you can actually get the age of the universe. So like I showed you, is if you have this object, one object going away from you, you will see it redshifted. And if it is coming towards you, you will see it blue shifted. And that's nothing but the Doppler effect, which you're already very familiar with. And this is what is called the cosmological redshift. That because of the expansion of the universe, what happens is you are seeing light from these objects getting redshifted, right, towards longer wavelengths. And if you measure the shift, right, delta lambda by lambda is equal to v by c. That means that will give you the velocity of the object. And what Hubble actually found was that the velocity was directly proportional to the distance of the object. So v, he said, is proportional to distance, which then he said v is equal to h into d, where h was Hubble's constant. And that's what he determined using the observational data which he collected. So if you look at this image over here, it's not very impressive, but here you have velocity versus distance, and the slope is Hubble's constant. Though you could see that in Hubble's time, actually, he had a very large scatter, which he got. In today's time, if you were to submit a paper like this with this kind of scatter and say this is a straight line fit, it would probably get rejected. But he was lucky that in spite of the errors, his results were correct. So if in a modern time, if you were to actually take these measurements, they'll better sit on the straight line. But in Hubble's time, they were not sitting. So it was his genius where he actually fit this to a straight line, and the slope is what we got Hubble's constant. And 1 upon the slope is the age of the universe. And so what happens is, if we want to look back in the universe, supposing we want to look back in time, right? You basically need to look back at longer and longer wavelengths, right? That will give you at what redshift will you be able to see. So what happens is, because Webb is looking at the infrared, you can actually go to a larger redshift because you are actually going back in time, right? And therefore, if you actually see this, if we look at ground-based observatories, they are smaller ones, and since these are the bulk of these are optical, if you're looking back in the universe, you can barely go back to an age of about 6 billion years. You can go earlier back to 6 billion years. With the Hubble telescope, we could go back to an age of about 1.5 billion years before present times. The Hubble Ultra Deep Field, which is also by the Hubble Space Telescope, a longer exposure, we went further back in time. And now with the James Webb, we are going to go to a redshift which is greater than 20, right? So the redshift is telling you what is the shift of this, of the wavelength, which is in principle a measure of time. That means how much back in time are you going back in the universe, right? And that's what actually happens with using infrared, and it's both the effect of using infrared, number one, and number two, of using a larger telescope, which has a larger mirror, 6.5 meters. So you are actually going to observe much fainter objects, right? So we are going back much here because these are much fainter objects also, which we can. So it's all the advantage of a larger mirror size, of going in space and looking in the infrared, right? So with that, so in that way, James Webb can satisfy its purpose of actually looking back in time. So here's another example of redshift. So you are actually seeing that if you had a redshift at 5.74, you will have the same spectral line over here, which if it was at redshift 8.42, you can see that the spectral line has got further shifted towards the red, longer wavelengths. So what is basically done is, supposing these are a whole bunch of galaxies you were observing, you can actually, these are stars, but if you were supposing looking at galaxies, you would look at different galaxies, measure the redshift, the delta lambda, which you're going to get, right? The same spectral line is getting shifted, and you can measure the delta lambda, and with that you can measure the redshift. And when you're measuring a redshift, you're basically going back in time. So here you're going to look at a galaxy which is much earlier in time compared to a galaxy which is more recent, right? So in that way you can convert. So I'll just try to repeat, why do we look for infrared? Is because infrared lets us, number one, look at dusty regions. These are called extincted regions in astronomy, which are dusty regions. For example, even the center of our galaxy, it has a lot of gas and dust. So if you were to look at the center of galaxy in optical, you will not be able to see very well. But if you were to look at it in infrared, you can actually see it very well, because the like I told you, the scattering is inversely proportional to wavelengths. So if you want to look at the center of the galaxy, you look at it in infrared. You can look at it in radio. Radio is even longer wavelengths, which you can see the center of galaxy with. And the other advantage is you can look at very high redshifted objects, because high redshifted objects will have their optical wavelength shifted to longer wavelengths, which are in the infrared. And therefore, by doing this, by infrared, you can calculate and you can find out that, say, redshifts 20 types objects will be emitting optical light in infrared, mid-infrared, far infrared. We can also, if we are looking at even exoplanets, right, which are which are planets in other systems, many of them lie in what are called the debris disks, or the disks around very young stars. Again, these are very dusty regions. So one of the other purposes of James Webb is actually to look for exoplanets, that is planets around other stellar systems, where there's going to be lots of gas and dust, and the infrared will let you actually see through it. And therefore, you can actually do that. So what James Webb is to do is look at targeted objects, right? So if you were to look at the same region, say with Hubble, you can see in optical, this is all gas and dust. You can barely see, I don't know, 4 stars or 5 stars. And if you were to look at it infrared, because there's dust over here, infrared light passes through dust. So yeah, you can't even count the number of stars you can observe in infrared. While in optical, you can barely observe these 4 or 5 stars. In infrared, the number straight away increases because it can look through the gas and dust, right? So this is another repetition of, this is the wavelength coverage of HST, wavelength coverage of Spitzer, and you can see that the James Webb is covering more of the Spitzer area, a little bit of the Hubble area also, because it's covering optical also and infrared, right? Okay, so just a slight repetition, like I said, that James Webb in principle is the successor to Herschel. Herschel is a 3.5 meter telescope, which basically looks at emission coming in the far infrared, 55 to 670 micrometers. And in that way, it's a very good instrument to observe young regions, dusty regions. Webb is going to observe in 0.6 to 28.5 micrometers. So an overlap with Spitzer and Hubble, right? Now, one of the chat questions is why does JW, this is by, who has asked it? Aditya Shukla. So Aditya Shukla has asked me, why does James Webb has 18 mirror segments? Okay, now there's a very simple answer to your question. The thing is, obviously it was realized that James Webb was obviously planned to be larger than Hubble, right? But the launch vehicle, the Ariane 5 vehicle, which was used by ESA, the European Space Agency, for launching, you can imagine a 6.5 meter telescope, right? That's really very large, right? And the one problem is that making a 6.5 meter telescope from a single mirror is difficult, right? How do you make such a large mirror? And the other problem is that such a large mirror could not fit on Ariane 5 rocket. And therefore, what was decided is that the James Webb is made up of hexagonal segments. Each of them have a 1.3 meter size, right? And it's interesting, this is a telescope which actually folds. So how do you fit it on Ariane 5, on the rocket? You can fit it by folding it, right? And therefore, the mirror is basically made up of these 18 segments, which, number one, like I told you, in terms of production, it's easier to produce 1.3 meter segments, right, than producing a 6.5 meter. And number two, launching a 6.5 meter, the Ariane 5 rocket, which is there of ESA's main thing, which is there, it cannot fit a 6.5 meter. So you need to fold it. And therefore, that was the simple solution to sending the thing, was let us have a folded telescope. And that's why that explains even the title of my talk, where I said unfolding, because there are many interesting engineering feats in James Webb. One of the most interesting one is that you have a folded mirror, right? I mean, you have a folded mirror which you will unfold and then open it up, right? So that's the basic reason for having your 6.5. Now, the hexagonal pattern, some of you all who are physics students, you all know something called the packing fraction, right? That is, supposing I want to collect pieces together. Supposing I have a box in which I put balls inside, right? You know that if I put balls inside it, there's going to be some part of the container which does not get used, right? And therefore, if I call the packing fraction is what is the volume of all the balls I fit inside divided by the total volume of the box, right? So what do I know? That if I have smaller balls, I can fit them much better and my packing fraction can improve. Otherwise, like you've studied in crystal physics, you have a 60%, 70% different packing fraction depending upon how you actually pack your balls, right, in the unit cell in crystals. Now, if you actually have hexagonal pattern, you can see that in principle, you cover the whole area. You don't have gaps. Very much before, I showed you all an image of the GMT, which is a telescope made up of 7 mirrors. And if you remember, the 7 mirrors are placed like that, and there are gaps between the mirrors. Because if you have circular mirrors, you can't make, say, 7 circles touch each other without gaps, right? So hexagonal gives you the advantage of making these segments in such a way that your gap is minimized. So if you look at the mirror over here, you see that the gaps are very much minimized between the segments. So we have the advantage of putting the segments because that's easier to build and it's possible to launch. But because they are hexagonal, the advantage we are getting is we don't have gaps, right? So Aditya Prasad, that's the answer to your question, that the hexagonal shape, and as well as Aditya Sagar, that the hexagonal shape will, fill up the whole area. There's another question which was there by Monica Sharma. Oh, sorry, by Gajraj Sharma. How far will the James Webb will be able to tell? See now the question is not, when you're talking about a telescope, you don't talk about how far. You talk about how faint. Okay, because for example, there can be an asteroid which is very close to the Earth, but because it's very faint, you do not see it very well. Asteroids are not emitting light, they are just reflecting light. And therefore, you could have even a 6.5 meter telescope which does not see the asteroid which is so close to you, right? But if you have a bright object at if you have, so a faint object close by may not be observable, but a bright object far away may be observable. So for any telescope, you don't ask the question of how far will you be able to see, but how faint will you be able to see. But like I showed you in that earlier plot, that we expect to actually see galaxies up to a redshift of 20, right? So I can actually, if you remember in that plot which I showed you, which was these things away, I'll just show it to you. You can actually, there is a plot of the differences, with redshifts, and you could actually see. So this is redshift 20. I think there was a plot which will tell you. So you can see that the James Webb is actually going to go almost to the time when the universe was only 0.3 billion years, right? So you're going to go almost to the very early universe, right? Compared to, for example, the Hubble Space Telescope. So you're going back very much in time. Yeah. So you can see over here, you're going back to this kind of an age, right? When the universe's age, right? You're going back in this way, So you're going back to redshift greater than 20. Obviously, it varies depending upon the brightness of the object, right? So obviously with this thing. Yeah, so Purtas is saying that the hexagonal pattern is very similar to honeycomb. Exactly. So it's even called a honeycomb design because it is genuinely like a honeycomb. But like I said, the advantage of that is because it packs it without these gaps. You minimize on the gaps, right? You don't want to have open parts of your mirror which are not reflecting light because you lose that light, right? So what does the thing has, this is one of the segments, 1.3 meter segment. There's a secondary mirror also, which is there. And there's a tertiary mirror. We won't go into all these details. This is the secondary mirror. So there's the primary mirror, light comes in, gets focused and gets reflected by the secondary mirror. Okay. Now, the very important component of the telescope is the sun shield. Why is the sun shield so important? Is because this is observing in the infrared. I will come to that in a bit. You can see that over here. We actually need the telescope to be very, very cold. Okay, we need the bulk of the telescope will be buried at a temperature 30 degrees above absolute zero. And there is one instrument which actually needs a temperature of 7 degrees above absolute zero, right? And therefore, what happens is you need to shield the telescope from the sun. That's the other very important part of the telescope. We don't want the telescope to get any sunlight, not even any earth light, right? Because the earth is also going to emit in the infrared. So we do not want that also to happen, right? And therefore, the telescope has this sun shield, which is basically made up of 5 layers. And each layer is as thin as a human hair. And it's constructed from a very special material called Kapton E. These membranes are specially coated with aluminum on both sides and doped silicon, etc. And basically the idea is to give you a temperature on that side for the telescope, which would be barely 30 degrees above absolute zero, right? So it needs a temperature of 36 absolute zero, right? And that's a very important part because of the infrared thing, because you want to measure infrared radiation. For any infrared telescope, you need to cool it. It is essential to cool it. And the cooling is happening partially with the sun shield. And the size of the sun shield is huge. It's 20 meters across. It's the size of a tennis court is the size of these sun shield. Again, the sun shield cannot be put in its open form when you're launching it. So the sun shield was also folded. And then the unfolding had to take place also of the sun shield. So actually the sun shield unfolding happened before the telescope unfolding, right? So before exposing the telescope, the sun shield was folded and launched. And now because we need to protect the telescope from the sun, we actually have, it was launched at this point, which is called the L2 point. Now, if you see the sun-earth system, there are 5 points in which are called where the gravitational potential is 0. So these are the points where you can actually launch and keep satellites which can stay in a stable orbit. And therefore, if you were at L1, L1 will always look at the sun. So L1 is not a good point to put an infrared telescope. Infrared telescope is always kept at L2 because L2 does not look at the sun. You have the earth coming in between and it's always kind of shielded by this. You do not see the sun. Plus you have the sun shield. So whatever little light comes also will get covered, which will get shielded by this is the sun shield and here's the telescope. So Hubble, just to keep you informed, Hubble is at a very close distance. It's only at a height of about 570 kilometers. And that's why we could have so many servicing missions to Hubble, because it's, it's very close by. But the James Webb has been launched to this L2 point, which is at a distance of 1.5 million kilometers. And that's where James Webb is sitting. And therefore, servicing missions also to James Webb would be very, very difficult. It would mean a journey through 1.5 million kilometers. James Webb itself took a month to reach there, right? While Hubble is very simple to go to, right? Okay. So this was a little earlier that you actually had Hubble going. So if you want to actually see where is Webb at any point of time, it is on the path which is, not this facing the sun. So if you look at the moon in the sky, say this is the crescent moon, it's crescent because the sun is over here. So if the sun is over here, James Webb is going to be on that side, right? So if at any point of time you want to look and identify where is James Webb, there are already telescopes on the Earth which actually have been tracking James Webb. It is going to be at the side opposite to the moon, opposite to the sun. So if you have the crescent moon, this side is where James Webb is. Or if you have a half moon, the sun is here, so therefore James Webb is over here. So you can actually see James Webb. There are actually images taken by observatories of James Webb, right? So James Webb has, I'm sorry, I think I'm running a little late in time, but I'll just hurry up. You have various instruments on the James Webb. There's an infrared camera, there's a MIRI instrument, as well as all these instruments. We won't go into the details. This is the sun shield, this is the primary mirror, here's the secondary mirror. And here are more details about the different instruments which are there on the telescope. And so in principle, James Webb is a true engineering wonder. If you see the kind of instruments that are there, the way it was launched, the way it was designed, the way it has been planned is really amazing. It's a true engineering wonder. We do not have much time, but you can actually, there are loads of images which you can find on the net of this, okay, and videos. I won't go into these things. So after James Webb was actually built, it was sent to French Guiana. This is in Kourou, where the launch site was there, via a boat, a barge rather, which actually took it from California through the Panama Canal to this French Guiana. Like I told you, it's at the northeastern coast of South America. And that's when it was launched, right? It was the Christmas Day thing, the event on Christmas Day, where you actually had the launch taking place. Like I told you, the first thing happened was the sun shield was deployed. The sun shield, within 5.5 days, the sun shield was opened up. And then within 9 days, you had the primary mirror actually opening up, and then the secondary mirror opening up. And it actually took 1 month to reach the L2 point. So before it reaches L2 point, there are a whole bunch of things which had to happen. The sun shield had to unfold, the 17 segments had to open. So in principle, it's like having, the 18 segments, it's like having 18 mirrors, right? And then what is planned for the next 5-6 months is that these mirrors have to get aligned. The cameras have to be cooled such that you reach this temperature of about 40 degrees above absolute zero. And the MIRI camera has to come to 7 degrees above absolute zero, for which it actually has some cryogenic fluid kept over there for cooling. So that was the launch. I hope you all saw it on Christmas Day. If you didn't, it's available on the net. You can see how it actually got deployed. I'm not showing you these videos because we don't have the time, but you can actually see it actually unfolded. So there was unfolding of the sunscreen, unfolding of the primary mirror, as well as the secondary mirror and the whole thing, right? So you can actually see the deployment sequence. This was the last image we have of the James Webb when it was launched. And this is still in the packed condition. And later on, what you must have seen recently, which came out, was the first image which came out, where you actually had all the 18 segments giving images of a single star at these different positions. The next job was to identify which mirror gave which image. Now, under each hexagonal bit, you have these accentuators, which are basically made to adjust the segments, because finally you want all these segments to add up to give you a mirror. And therefore, that is what is called mirror alignment. So if you look at these things are there under each segment, and they will adjust the alignment. Now, the alignment obviously has to be of the order of the wavelength of light, right? So you need it to be aligned to the order of that and even smaller, so that you have a perfect alignment of the mirror. So that is a very long process. So the next 6 months, 5 months, next 3-5 months are dedicated just for mirror alignment and cooling of the instruments. And that's exactly what now James Webb is doing. They're working on the mirror alignment, and mirror alignment has been going on very well. We already have an image of the combined image coming from all these different segments, so that they all have to overlap together to give you one image. Otherwise, the earlier image was the one I showed you, which had 18 different images, right? And so there are a whole bunch of early science programs which are planned in this period itself. First of all is to look for exoplanets. So direct imaging is difficult. It can be done only for the closer ones, but spectroscopy to characterize their planetary atmospheres, look at debris disks around stars, solar systems and formation, whole programs with stars, with looking at galaxies, with looking at dark matter. And then in all these large telescopes, you have what is called director's discretionary time, which is if there's something very urgent, something very interesting, then you can actually observe it. So there's about 460 hours of observing time. The normal democratic way in science is you actually give proposals. So any of you, me, any of us, we can actually give proposals for observations with the James Webb. And if the proposal is considered good enough, you can actually get time to observe with this $11 billion telescope. It's open to everyone. Like I said, that is in the spirit of science, that there are announcements for proposals for their deadlines, and you can actually put in proposals for things you want to observe. If the proposal is considered good enough, you are actually given time. So you can actually observe with the thing. The future is interesting. There's going to be another telescope which will be launched in 2027, which is the Nancy Grace Roman telescope. And a whole bunch of other telescopes. There's the Super Hubble, Euclid telescope. And definitely this is a very interesting time to live in astronomy, because you have a large number of telescopes which are being launched. You can see really cutting edge technology, which is going hand in hand in actually building these telescopes, right? It's very high technology. I did not get the time to talk about it because I was focusing more on the science of the telescope, but be aware that it's very high technology, very high engineering that has been instrumental in actually building a telescope of this kind. So thanks a lot. I'll stop with this. I'm sorry I overshot, but I can have a look at the, Monica, if you permit me, I'll just have a look at the questions.
Yes, ma'am. I'll hand over to Dr. Rita to take over the question and answer session round.
Okay.
But I would like to thank you, ma'am, for such elaborately telling us about the need for these telescopes. Thank you, ma'am, for such a very informative talk.
Welcome. My pleasure.
Dr. Rita, you can take.
I'm sorry, I already took some of the questions because I saw.
Yes, ma'am. Yeah, ma'am.
I took it, but yeah, you can continue.
Thank you, Monica, ma'am. Am I audible?
Yes.
Yeah. Thank you so much, ma'am, for such an interesting talk. We really enjoyed it thoroughly. And some participants have asked some questions. With your permission, can I read this question for you?
Please do.
Yeah. First question is, ma'am, from Ashwani Kumar Singh. That is, we see lot of colors in images recorded by these telescopes while being operated in IR or UV region. How they can record colorful images, as color is something between 400 to 800 nanometer region?
Yeah, thanks. So that's a very nice question, Ashwini Kumar. Very good question. So actually, in principle, these are artificial colors, right? So obviously, these emissions are not what we can detect with this thing. But what they generally do is that in those images, the longer wavelengths are obviously shown more in red, shorter wavelengths are shown in blue or in violet. So for example, if you see the Chandra images, right, X-ray telescope images, you'll see that there are parts which are blue or violet, which are the ones which are the high energy parts, while the redder parts are the ones which are the low energy parts. So in principle, these are artificial colors. So you're absolutely right. The colors are not genuine colors. These are colors which are coming because of artificial coloring. But like I said, we generally code it in such a way that shorter wavelengths are blue or violet and longer wavelengths are red. So it kind of gives you an idea of what is the color, right? What is the thing? Yeah.
Thank you, ma'am. Second question is from Aditya Prasad. Can we produce images with a non-connected lens, or if the parts of the hexagon were dispersed and create a higher virtual radius?
Okay, so you can. So one is, I think you're talking about the parts of the hexagon. So that's what I'm saying, is that that's why under each segment there are accentuators which are used for what is called mirror alignment. So that's exactly what James Webb is doing now, that they need to very precisely align all these hexagons to give you a single mirror. If you don't align it properly, then you'll end up with multiple images. So it was in the first initial stage, you remember I showed you that image which had 18 different points on it. So that is when it was totally disaligned, right? But if you, so any mistake in the alignment will create multiple images. So in principle, what you're saying, you can produce not a non-connected lens, it's a non-connected mirror, right? This is a mirror, not a lens. Lenses you can't join like that. Mirrors you can join. So you can create a non-connected mirror by adding on all these pieces and adjusting them so that they fit exactly. It's like you had a mirror which broke, and then you adjust it so that all the pieces join together to give you that image, right? So in that way you can do that. The other method which is used, which I showed you when I showed you the image of the Keck telescope. So I did not show you images of VLT, where we actually do what is called interferometry. So you can do interferometry also in optical to get better resolution, right? So in that way, with interferometry, there is, there's a method which is called aperture synthesis, with which you actually artificially synthesize a larger aperture, right? So that is which is actually used commonly in radio. In radio astronomy, it has been used a long time, but now it's also being used in optical with the VLT as well as with the Keck telescopes. Yeah.
Okay. Thank you, ma'am. So there is a question from our faculty member, Dr. Bijmohan. To focus shorter wavelengths coming from celestial bodies, which kinds of lenses used? Are they magnetic or something else?
No, so actually, no, these are, actually the problem with shorter wavelengths, right, is that, for example, if you're doing it in X-ray, right, in X-ray, there's a technique which is called grazing incidence. That means because at X-ray, at shorter wavelengths, the wave nature is less pronounced of light, right? It behaves more like photons, right? So you're actually getting more of counters. So X-ray telescopes have more of counters, yeah, like they are counters compared to, they they observe light more as particles than as waves, and therefore for X-rays you have something called the grazing incidence method, which is used for focusing. But focusing is all via optics. There's no magnetism used at all. It's only optical. It's done through optical, these things. Yeah.
Okay, Thank you, ma'am. So, one question is from my side.
Yeah.
Ma'am, one thing I want to ask, that the purpose to choosing the Lagrange point 2
Yes.
for this JWST telescope is only to shade sunlight or something else? Means there may be many other points on which we can avoid sunlight. Like you said that gravitational potential must be 0.
Yeah. So thanks. That's also a very good question. So the problem is, like I said, is that essentially it is to shade the telescope, because the problem is, for example, Hubble is only at 570 kilometers, right? So Hubble is going to feel the night-day cycle. You are going to get the day-night cycle. It will get, you will have all those effects coming in. And James Webb, since it's specifically looking for infrared, right? Earth itself is a very strong infrared emitter. So the problem is you want to shield it not just from the sun, but also from the earth also. Earth is also problematic. So if you cannot put that telescope so close to the earth. Otherwise, you'll have to have some other cooling mechanism to cool the telescope. So all these, I did not mention it, but for example, I did. Gaia, for example, is also sitting at L2 point. Herschel telescope, which also observed in infrared, was also at L2 point. So L2 point is the best way to defend it from emission coming from the earth as well as the sun. So in a way, it is almost as though it's in the shadow of the Earth, because the sun, you have the Earth, and you have these things. Like I said, right? That's why you can always say, where is Webb sitting? Because you just need to know the opposite direction of the sun. So Webb is always going to be protected from the sun, because if it gets exposed to the sun, then it's gone. Then the whole thing is finished. So basically, it is for shielding, number one. And number two, the problem is you want your telescope to sit there in a kind of stable orbit, right? Now, the orbit is still not yet very stable, in the sense they constantly have to do, little boosters to maneuver the orbit so that the thing remains stable. All these satellites, what happens is they don't just sit at a point, they have an orbit. Okay, it's called a halo orbit, so it actually slightly moves in that area. Your principal Rajiv Agarwal is in celestial mechanics, so he'd know that you have that orbit. So then what happens is the telescope has to be constantly given boosters to adjust the orbit. So you have to constantly adjust the orbit, but those adjustments are small, not very large. But on the other hand, if you had it in another position which was not stable, where there's some gravitational potential, then you'll have to constantly do a lot of maneuvering to keep it. So with L2 point, you have minimum amount of maneuvering. Little bit of adjustment is there, adjustment, but not so much, because that point has zero gravitational potential. It's balanced, right? So that's both the things are there. One is the shielding, and number two is it's a stable position. You can keep it there for a long time without much problems. Yeah.
Okay, thank you so much, ma'am. And there is one more question from our another faculty member, Dr. Yogesh Kumar. Can we capture some pics of nebula and other white dwarf star, etc.? Find pictures to see deep inside of these objects.
Sorry. So you can get pictures of nebula, yes. That you will get very well with James Webb, because James Webb is an infrared telescope, and nebulae in principle have a lot of gas and dust. So you cannot see nicely through optical, you will see it very well through infrared. But in principle, for example, a white dwarf, you cannot look through the white dwarf, right? Because the white dwarf is made up of, it's like you're trying to look through an iron ball. You cannot look through it, right? So you cannot, it's not going to give you pictures to see deep inside a white dwarf, for example. You won't do that. Yeah.
Okay, thank you, ma'am. Thank you so much for taking the question so nicely. So I'm for further program, I'm handing over again to Monica, ma'am.
Thank you, Rita, ma'am, and thank you, Dr. Priya, for taking all the questions. Now I would like to request one of our faculty, Mr. Ajay Pratap Singh Gehlot, sir, to give the vote of thanks. Over to you, sir.
Hello, I am audible?
Yes.
Yes, sir.
Okay. On behalf of Physics Department, Deshbandhu College, University of Delhi, I am very thankful to the speaker of the day, Dr. Priya Hassan, for enlightening us about the mysteries of universe and the various types of astronomical telescopes in such a simple and informative, impressive way, and especially about the James Webb Space Telescope. I thank you, madam, for the bottom of my heart, for taking time from your busy schedule to be the guest speaker at our webinar. All thanks to your enlightening words that inspired so many people out here. Thank you. I also thank our governing body chairman, our visionary principal, Professor Rajiv Agrawal, and our vice principal, Professor Kamal Kumar Gupta, for providing us the motivation and opportunities for organizing such events for the benefit of science community. I also thank our IQAC coordinator, Dr. Aditya Saxena, our DBT Star College Project Coordinator, Dr. Indrakant Singh, and our teacher in charge, Dr. Kakuli Bera, for their help and guidance. I also thank all the teaching fraternity and staff members present here for their gracious presence and sparing their valuable time. And I also thank my departmental colleagues for their hard work and all the pain they have taken for the success of this webinar. And last but not least, it is our students who are our real target and audience of all such webinars, whose presence make the success of such webinars. So a big thank to all of you And so thanks one and all present here once again.
Thank you, sir, for your kind words. Again, I just like to thanks Dr. Priya for this informative talk. Thanks from all of us, and thank you all the participants. The session can be closed. Have a good day.
Thank you, ma'am. Thank you. Thank you, sir.
Thank you.
Thank you. Thank you.